In Activity 7, Surface Currents, students learn how surface currents form and what affects their direction. They first model the formation of a surface current, then observe what happens when they are interrupted by landforms. Finally, students discover how Earth's rotation affects their movement. You will need the following materials from the kit. Activity Sheet 7, Parts A, B, and C. Plastic plates, plastic straws, reclosable plastic bag, 12-inch cardboard circle, container of cinnamon, modeling clay, plastic knife, world map, Northern Hemisphere resource sheet, Southern Hemisphere resource sheet, and sand. You will also need to provide pencils, bucket, blue crayon, red crayon, globe, paper towels, pitcher, and tap water. To prepare for Session 1, make a copy of Activity Sheet 7, Part A for each student. Fill a pitcher with tap water. Make sure to have a bucket on hand into which students can empty their plates of water. Each team of 4 will need 1 plastic plate, half stick of modeling clay, 4 plastic straws, and small amounts of cinnamon and sand to sprinkle into their plates of water. Make sure to have paper towels available just in case of spills. To begin Session 1, inform students that a current is a steady flow of water within a larger body of water, and that unlike waves, currents move water from place to place. Inform them that there are 2 kinds of currents, surface currents and density currents. Students should presume that surface currents are located on the surface of the ocean. Distribute 1 plastic plate and 4 plastic straws to each team of 4, and pour tap water about 1 centimeter deep into each team's plate to represent the ocean. Have students sprinkle a small amount of cinnamon evenly over the surface of the water. Make sure to point out that the cinnamon floats. Then instruct students to blow gently across the surface of the water with a straw. This action creates ripples and pushes the water, as evidenced by the cinnamon moving with the water across the plate. Tell students to blow across the water again from another direction. This will cause the water flow to change direction and move in the direction of the airflow. Then identify the ripples for the class as surface currents. Ask students, what do you think causes surface currents to form in the ocean? Students should infer that wind causes surface currents. Explain that prevailing winds are global wind systems caused by the uneven heating of Earth's curved surface. These prevailing winds blow continuously across the surface of the Earth and push against the surface of the ocean, setting ocean currents in motion. Next, give each team about a teaspoon of sand and tell them to sprinkle the sand over the plate of water. Make sure to point out that unlike cinnamon, the sand sinks. Instruct students to blow across the water again. Students will note that the sand sits at the bottom of the plate and does not move across the water like the cinnamon did. Ask students, what does this tell you about the depth of surface currents? Guide students to understand that the surface currents affect only the surface of the water and that the deeper water is not disturbed. These surface currents can be hundreds of miles wide and thousands of miles long, but are relatively shallow, only 100 or 2 meters deep. Next, distribute Activity Sheet 7, Part A. Ask students, do you think currents flow in a straight path across the ocean? Instruct students to blow across the water again and observe what happens when the water hits the curved edge of the plate. Make sure to point out that the water turns. Ask students, what do you think happens to ocean currents when they run into continents? Students may suggest that landforms such as continents, islands, and reefs are obstacles to currents and change the direction of their flow. To demonstrate this, have students dump out the water and dry their plates. Distribute half a stick of modeling clay to each team and have them make landforms and stick them to the plate. Then instruct students to draw the outlines of their landforms onto the circle diagram on their activity sheets. While they are doing this, refill their plates with water. Next, add cinnamon again to the water and have students blow across the water. Tell them to draw arrows on their activity sheets to show the direction of water flow around the clay landforms in their plate, and to mark with an X the position from which they are making the wind blow. Ask students what happens to the surface currents when they run into landforms. Students should note that the currents change direction, then flow around the landform. Finally, let students know that they will learn another factor that causes currents to change in Session 2. To conclude Session 1, discard the water and straws, collect the clay, and store it in a reclosable plastic bag. Wash and dry the plates and return them, along with the other materials, to the kit. To prepare for Session 2, make a copy of Activity Sheet 7, Parts B and C for each student, and make a copy of the 2 hemisphere resource sheets for each team of 4. Make sure to have a globe and the physical map of Earth available for students to examine. Each team of 4 will need a copy of both resource sheets and 2 pencils. To begin Session 2, distribute a copy of Activity Sheet 7, Part B to each student. Explain that the diagram on this activity sheet shows some of the major surface currents in Earth's oceans. Ask students, what do you notice about these currents? Help students understand that the currents seem to move in large circles. Then ask, what do you think causes the currents to move in circles? Students should recall from Session 1 that prevailing winds and bumping into continents or other landforms causes currents to change direction. Hold up a globe and slowly turn it from west to east. Remind students that Earth rotates on its axis. Ask, what effect, if any, do you think this spinning motion has on ocean currents? Students may suspect that it causes them to change direction. Accept all answers. Place a 12-inch cardboard circle on a desk or table and use a pencil to pierce the center of the circle. Secure it so that you can rotate the circle by moving the rim and hold the circle still. Have a student stand opposite to you and use the red crayon to slowly draw a straight line from the center of the cardboard circle to the rim. Next, slowly spin the circle in a counterclockwise direction. Instruct the student to use the blue crayon to try to draw a straight line from the center of the circle to the rim. Ask, why do you suppose the first line was straight and the second line was curved? Students should understand that spinning the circle caused the line to be curved. Explain that you have just demonstrated the Coriolis effect, a phenomenon that was first explained by the 18th century French mathematician Gaspard de Coriolis. Coriolis correctly theorized that the rotation of Earth on its axis causes air and ocean currents to stray from their original straight path. Because Earth is round and spins on its axis, areas along the equator, the widest part of Earth, move much faster than areas north or south of the equator. This causes the currents to bend slightly. Instruct students to examine the diagram of the ocean currents on Activity Sheet 7, Part B. Then distribute the Northern Hemisphere resource sheet and 2 pencils to each team of 4. Tell students to label the equator, North Pole, and the continents. Then encourage students to imagine that they are looking down on Earth from above the North Pole and ask, from this vantage point, in which direction would Earth appear to be spinning? Students should respond that the Earth would appear to be spinning counterclockwise. Next, using a pencil, pierce the paper at the dot labeled North Pole and hold the paper flat against the desk. Slowly turn the paper counterclockwise and draw a line from the North Pole straight to the equator through the ocean area. Then draw a line from the equator straight to the North Pole. Ask students, what did you notice about the lines you drew? Students should note that the lines drawn from the North Pole to the equator curve to the left, and that the lines drawn from the equator to the North Pole curve to the right. Have students look at the currents on their activity sheet that are north of the equator and ask, in which direction do you think the ocean currents in the northern hemisphere move? Students should identify the direction as moving clockwise. Instruct students to add arrows to the lines to show the direction in which currents in the northern hemisphere flow. Then distribute the second resource sheet, the southern hemisphere on Earth. Tell students to label the equator, the South Pole, and the continents. Ask students from this vantage point, in which direction would Earth appear to be spinning? Students should respond that the Earth appears to be spinning clockwise. Pierce the paper at the South Pole with a pencil and use the pencil point to hold the paper to the desk. Slowly turn the paper in a clockwise direction and draw a straight line from the South Pole to the equator through the ocean areas. Then draw a straight line from the equator to the South Pole. Ask students, what did you notice about the lines this time? Students should note that the lines drawn from the South Pole to the equator curve to the right, and that the lines drawn from the equator to the South Pole curve to the left. Have students look at the currents on their activity sheet that are south of the equator and ask, in which direction do you think ocean currents in the southern hemisphere move? Students should say that the ocean currents would move counterclockwise. Instruct students to add arrows to the lines to show the direction in which currents in the southern hemisphere flow. Distribute a copy of Activity Sheet 7, Part C, to each student, and tell them to use the maps they have just completed to answer questions 1 through 3. Review their answers as a class. Finally, inform students that in the next activity, they will learn how density currents form and how they move. To conclude the activity, post or discard the resource sheets. Return the master sheet to the kit. For science background, reinforcement activities, curriculum connections, and information about the Delta Science Reader, please consult your DSM Teacher's Guide.